Okay, so now we're going to go step back to our nice one-dimensional universe, life on the x-axis. And we've got our 2 points here still, P and Q. We have our origin back here somewhere. And so we looked at how to calculate the distance between these 2 points. So now we can specify distance. But there's something else we need to figure out how to do. Suppose I have a body, and I'll just represent that body as a square, and we'll call that body B, B for body, and I place that on this one-dimensional axis. Well, we know that it has a location, and we just choose its midpoint here, and we'll say x of B. That's the location of our body B. But what if B doesn't sit there? What if B is moving? What if B is moving in this direction on the x-axis, moving at a uniform velocity? How can we figure out what that velocity is? How can we label that velocity and quantize that velocity so that we can make some sense out of it? Well, simple way to look at it is distance and time. When you're in your car and you're driving and you look at your speedometer, it registers your velocity, your speed, in miles per hour, which is miles divided by hours. And that is simply distance divided by time. So if you travel a particular distance in a particular time, and you divide how far you went with how long it took you, that tells you your velocity v. So in our little thought experiment up here, if I have a body B and it's traveling at a uniform velocity, and it crosses, it comes down here and it crosses P, and then it moves on, then it crosses Q, and then it moves on. We can say that the time that it crossed point P, we can call that T sub P, and the time that it crossed point Q, we could call that T sub Q. And we know that P has location coordinate x of P, and Q has location coordinate x of Q. So we can take this relationship here and rewrite that for our one-dimensional universe, and we can say that the distance traveled, and we just did this, is x of Q minus x of P. That's how far we went. The amount of time it took is T sub Q minus T sub P. And that's our simple velocity. And that's velocity, that's at a constant velocity. So if I was driving from Houston to Dallas, I might write that the velocity from Houston to Dallas equals 270 miles, and it typically takes me 4.5 hours to get there. And if I multiply that out, I get 60 miles per hour. So my average velocity driving from Houston to Dallas is 60 miles an hour. But if you've ever driven from Houston to Dallas, or driven anywhere in Houston or in Dallas, you know that your velocity is not ever constant. It's changing all the time. So we need to look at a concept called instantaneous velocity. V, capital V, is our average velocity. It's your total distance divided by your total time. We're going to look at a instantaneous velocity, which is going to be a lowercase v, and v is a function of time, so we're going to call it v sub t. And all that means is that as you're driving, as time passes, your velocity changes. You speed up, you slow down, and you stop, and you start, and so forth. So the way we're going to represent v sub t, the way we're going to look at it, is in a two-dimensional space. And this is something that we do quite a lot. We're actually looking at a one-dimensional problem, but in order to do that, we need to go up one level of dimensionality to describe what's going on here. So I have a two-dimensional space. This axis is velocity. This axis is time. And I'm just going to mark this up. Let's say this is 12 noon, and this is 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m., 7 p.m., 8 p.m., 9 p.m., and so forth. And velocity, let's just say this is 20 miles an hour, 40 miles an hour, 60 miles an hour, 80 miles an hour. I get adventurous, 100 miles an hour. And I'm going to leave Houston at 3 o'clock. So I'm going to call this T sub H for Houston. And we know it takes me 4.5 hours to get to Houston. So 1, 2, 3, 4.5 is 7:30. So this is my T sub Dallas, T sub D. So what does my velocity look like? Well, obviously I'm sitting in my driveway, so my velocity is 0. Then I pull out onto Lakeshore Drive, and I am now going 20 miles an hour or 25 miles an hour, because that's our speed limit. Then I drive a little more than a mile, and now I'm on NASA Road 1. NASA Road 1, the speed limit's 45. So I'm on NASA Road 1 for a while. Then I get to Interstate 45, and I accelerate to the speed limit, of course, which is about 65. But I'm driving in Houston, so it's stop and go traffic, so traffic is going up and down, I'm slowing down, I'm speeding up. Sometimes it's bumper to bumper all the way to Dallas. When I come into Dallas, then I slow down. I exit onto Loop 12. Again, I'm going about 45. I get on Jim Miller Road, which is even slower. There's some railroad tracks. And I eventually get to Dallas. Oh, and look, I got here late because of all the traffic. But that's okay. You get the idea of what I'm trying to say here. So our velocity changes over time as we move from the first point to the second point. And so just for consistency's sake, I'm going to redefine my time in Dallas as 9 p.m. So now it took 6 hours. Sometimes it does take 6 hours. Again, it depends on the traffic. I'm still interested in my velocity, so I can calculate my average velocity, my capital V, and we know our distance is still 270 miles. My time now is 6 hours, and that works out to 45 miles per hour. That was a long trip. I did not expect it to take 6 hours. But that's one of the problems with instantaneous velocity, is you never know what it is or how long you're going to be at any one particular velocity. So, how do we calculate instantaneous velocity? Well, remember that our average velocity is our total distance for this case, x of Dallas minus x of Houston divided by t sub Dallas minus t sub Houston. And like I said, in this case, 270 miles, 6 hours, 45 miles per hour. But there's another way to figure out what our velocity is, and that's to look at instantaneous velocity. So, like I said, when I'm sitting at my driveway ready to go, my initial velocity, which we always denote as with a subscript 0, v sub 0, is equal to 0. I'm sitting still in my driveway. It doesn't have to be 0. I could have been driving from some other location into Houston and then into Dallas, so my initial velocity might not be 0, but in this case it's equal to 0. Then what we do is, instead of looking at the total time that we went on our trip, we restrict the time to what we call a neighborhood. So we look at the time it took to go just a very short distance, and we look at the velocity, the average velocity that we were going during that time. So neighborhood is a engineering and really a mathematical term for the portion of a signal or a waveform that you're looking at. But it also works for an analogy, because we start off in a neighborhood. So in my neighborhood, which is El Lago, I find that it takes me 1.2 miles between my house and NASA Road 1, and typically takes me 3 minutes to drive that. Speed limit's 25. I do this calculation, I find out that this equals 24 miles per hour. A little bit slow. Sometimes there's a squirrel on the street and you have to slow down. But in my local neighborhood, my velocity is 24 miles an hour. Like I said, when I get on NASA Road 1, my velocity jumps to 45 miles per hour, and so on. I can slice this even finer though. So instead of looking at a distance of 1.2 miles, the distance between my house and NASA Road 1, I can look at the distance between, say, where I cross Tallywood Road and Plantation Drive, which is about 0.3 of a mile. And I might find that I can do that in 35 seconds. Then if I do the math and conversions, I find out that that's equal to 30.86 miles per hour. Because I happen to know that between Tallywood and Plantation, the cops are never there, so I can go a little bit above the speed limit there and be okay. So we look at a finer slice, and we get a velocity for that slice. And we look at smaller and smaller slices till we eventually get down to a slice that has no distance. It only has a velocity. So that is becomes my instantaneous velocity.